8.5, the Cartesian equation of a plane. So just a little bit of recall. To find vector n, so like the normal vector, which we denote as a, b, and c, that is perpendicular to two vectors, vector a and vector v, we must cross product vector a and vector v. So this is how we denote right here cross product. Okay? So your cross product. Okay, the normal axis for the plane. So let's talk about the normal axis for the plane. And we've already talked about that. This is the only possible line that can be drawn through the origin that's perpendicular to the plane. Okay, so if the line is perpendicular to the plane but doesn't go through the origin, then it's just a normal to the plane, but the normal axis must go through the origin. Okay, that's what the difference is. So in the diagram below right here, ON is the normal to the plane. Sorry, plane. Okay, so ON right here is the normal to the plane because it joins from the origin, and it's, if you extended it, it's perpendicular to the plane. And that's going to be called the normal axis. Any non-zero vector is a normal to the plane if it lies along the normal axis. Okay, so any vector here is also obviously going to be a normal to the plane. Okay, so the Cartesian equation, that's what we're going to be focusing on in this section 8.5. So the Cartesian equation of a plane is just like the Cartesian equation of a line. It's just one more say letter. Okay, so we saw ax plus by plus c, but now what we're doing is we're extending this by 1, and we have cz plus d equals 0. Okay, so d is going to be that constant value now, whereas the Cartesian equation of a line, we saw c is the constant value. Okay, so the normal ABC is normal to the plane, and the normal is, of course, vector A cross vector B. Okay, vector A and vector V are two non-collinear direction vectors of the plane. Okay, so they cannot be lying on top of one another. So two planes whose normals are n1 and n2, okay, are parallel if and only if n1 and n2 are some constant, like some multiple of one another, and we denote that multiple with a k. Okay, k cannot be 0, so non-zero. Okay, two planes whose normals are n1 and n2 are perpendicular if the dot product of their normals equals 0, and they have an angle between the planes determined by this equation right here. Okay, so the point A is a point on the plane with this normal. Determine the Cartesian equation of this plane. So we know that the Cartesian equation of a plane is ax plus by plus cz plus d equals 0. And immediately we're able to sub in -1, 2, and 6. So -1, 2, and 6 for ABC. Okay? Now, because we know one point on the plane, what we can do is we can sub in 1, 2, 2 for the x, y, and z, and then we can just solve for d. So let's go ahead and plug that in. 1, 2, and 2. And let's now solve for d. So we have -1 plus 4 plus 12 plus d equals 0. What I usually do is I usually actually calculate the sum of these and then just simply bring it over. So 12 plus 4 and then -1. So -1 plus 4 is 3. So 12 plus 3 is just 15. So if we did 15 plus d equals 0, we can just simply bring the 15 over. D equals -15. So when we write out the Cartesian equation for a plane, what we want to do is we just want to sub in the A, B, C, and D. That's what we're looking to sub in. So -1x plus 2y plus 6z minus 15 equals 0. Okay, if you remember back in grade 9 when we did like the standard form, the standard form of a line, what we do is we have to make sure that, usually to be fully simplified, what we have to do is make sure that this leading coefficient is positive. So I'm going to take this entire equation and multiply it by -1. So our equation should really read positive x minus 2y minus 6z plus 15 equals 0. And that's what we should get for the Cartesian equation of this plane. I'm going to show you one more way to do this. This may look very familiar. It's going to be like the dot product form, and it's going to look familiar from when we did the exact same thing for the Cartesian equation of a line. Okay, so going back to the top, we know point A. Okay, and then let's call point B simply x, y, z. So if we wanted direction vector AB, what we need to do is say x minus 1, comma, y minus 2, comma, z minus 2. Okay, and that's going to be, if we have B as x, y, z, this is just the general form for a direction vector between like point B and point A. Okay, but what we know about the equation, or about a plane in the normal, okay, so this direction vector is a direction vector of the plane. Now what we're going to do is we're going to dot this with the normal. So we're going to go AB dot the normal, because if we have a direction vector laying on a plane, and then we have a normal going through the plane, these will be at 90 degrees. And what do we know about the dot product of two direction vectors? If they are 90 degrees to one another, they're going to equal 0. So we're going to go ahead and multiply -1 times x minus 1 plus 2 y minus 2, and then plus 6z minus 2. And then what we're going to do is we're just going to expand and then collect like terms. Okay, so expand, I get -x plus 1. I don't know why I put y here. Sorry, y minus, 2. I understand. 2y plus 2y. My 2's look like z's. My z minus 12 equals 0. So let's write the x, y, the y, and the z first. -x plus 2y plus 6z. Then we have 1 minus 4 minus 12. Okay, so I get for this one -15. Again, same as the last one, we want to multiply it by -1 to get this leading coefficient, the coefficient of x as positive. So it changes, it flips every single sign in the entire equation. And that is our Cartesian equation of this plane. Again, just a different method. Okay, example 2. Determine the Cartesian equation of the plane containing these 3 points, A, B, and C. So what we want to do first is we want to find two direction vectors, and then what we're going to want to do is cross them to find the normal. So let's take direction vector AB, and then let's find direction vector BC. Okay, and I just do them in order. I don't pick and choose anything. Okay, so I'm just going to do this. 3 minus -1 is 4. 2 minus 2 is 0. And then 4 minus 5 is -1. Okay, that one's done. BC, so we're going to go C minus B. -2 minus 3, I get -5. -3 minus 2, I get -5. And 6 minus 4, I get 2. Okay, so here are two direction vectors. Now let's simply cross them. So AB cross BC. I'm going to do this method, 4, 0, -1, 4, 0, -1, and then -5, -5, 2, -5, -5, 2. Okay, so 0 minus 5, I get -5. 5 minus 8, I get -3. And -20 minus 0, so -20. I get that as our normal. Okay, so remember, two direction vectors, cross them, you're going to get a normal. From here, everything is easy. Let's change colors. Okay, ax plus by plus cz plus d equals 0. So negative 5, let's do this in one step. So we can sub in the normal. Let's also sub in one of the points. Okay, so let's just go ahead and take like the first point, A. Negative 1 plus our B, where A, B, C are the components of the normal. Okay, so minus 3 times y, which is 2, plus, or minus 20, times 5, plus d equals 0. Sorry to jam it in there. Okay, 5 minus 6 minus 100 plus d equals 0. Five minus 6 is negative 1. Negative 1 minus 100, it's negative 101 plus d equals 0. Simply bring that over. D equals 101. So we can write negative 5x minus 3y minus 20z plus 101 equals 0 as our equation, or fully simplified, which is the more correct answer. You're going to get full marks for this, no marks off. Multiply this by negative 1. So 5x plus 3y plus 20z minus 101 equals 0. This is the correct answer. So as soon as you get into the rhythm of doing this, they get really, really easy, and you kind of just figure out what you need. Okay? So determine the Cartesian form of a plane whose vector form is this one right here. Okay, so we're already given two direction vectors. We know that we need a normal. So let's go ahead and cross these two. So let's go 102 cross negative 134. Okay, so I'm going to write 102, 102, and negative 134, negative 134. Okay, and remember what we do is we multiply and subtract. So 0 times 4 is 0, minus 6. So I get negative 6. Okay, negative 2, so 2 times negative 1. So negative 2 minus 4. I get negative 6. And now 3 minus 0, I get 3. Okay, here is our normal. So we know that this is the A, B, and C component of the normal. We have the point 1, 2, negative 1. Let's go ahead and sub it in. Sub in everything at once. Negative 6, 1, minus 6, 2, plus 3, negative 1, plus d equals 0. I get negative 6 minus 12 minus 3 plus d equals 0. So 12, 18, 19, 20, 21. Negative 21 plus d equals 0. So d equals 21. And we can simply rewrite the equation. Negative 6x minus 6y plus 3z plus 21 equals 0. But this is not fully simplified. So let's multiply this. We're having to do that a lot. Multiplying by negative 1. Minus 3z minus 21 equals 0. This is the Cartesian form of a plane whose vector form is this right here. So what we're going to do, I'm going to clear the board and then we're going to think backwards. We're going to determine the vector and parametric equations of the plane with this Cartesian equation. Okay, so let's go ahead and think backward. Okay, so we have the Cartesian equation. What we're going to do is we're just going to simply sub in any point for like x and y, and we're going to pop out a z point. So we're going to, what we're looking for is like 3 different points, and then we're going to start back at kind of where we were like 2 questions ago, where we have 3 points, and then we're going to solve for the Cartesian equation or the vector and parametric equations. So for the first point, let's sub in what happens when x equals 1, y equals 1, and then let's actually solve for z. Okay, so 1 minus 2, 1 plus 5z minus 6 equals 0. So let's go 1 minus 2 minus 6. Negative 7 equals 0. 5z. Okay, bring that over. I get z equals 7 over 5. Okay, and now you know what an easy one is? When we sub in 2, 0. So let's sub in y equals 0 and z equals 0. So this is basically finding the x-intercept. So x minus 0 plus 0, that's fine. Those go away. Minus 6 equals 0. So x equals 6. Okay, and let's sub in a 1 and a 0 in the cell for y. Okay, 1x minus 2y plus 0 minus 6 equals 0. Okay, that goes away. 1 minus 6 is negative 5. Bring that over. I get y equals 5 over 2. Okay, so there are 3 random points that lie on this line. Sorry, on this plane. Okay, let's call that A, just point A. Let's call that B, and let's call that point C. So now let's actually find 2 direction vectors. Okay, so let's find AB, direction vector AB, and let's find BC. AB, so we're going to subtract 6 minus 1, 0 minus 1, 0 minus 7 over 5. Okay, a little bit ugly with the fraction, but we can do it. All right, and BC, 1 minus 6, I get negative 5, comma, 5 over 2 minus 0, I get 5 over 2, 0 minus 0, I get 0. Okay, so here are our 2 direction vectors. Now that we have 3 points and 2 direction vectors, we can just simply sub these into the vector form of the equation of a plane. So what I'm going to do is I am going to write, okay, vector R, we need to write any one of these points, okay, 1, 1, 7 over 5, that's fine, 1, 1, 7 over 5, plus parameter S, any direction vector, so 5, negative 1, negative 7 over 5, plus T, and then any direction vector, negative 5, 5 over 2, 0. Okay, and for parametric equations, again, just take the x, y, and z components. So let's just draw a line down here, and we'll just separate this, x, y, and z components. So 1, 1, 7 over 5, 1, 1, 7 over 5. Then parameter s, 5, negative 1. So plus 5s minus s minus 7 over 5s. Okay, and now negative 5, 5 over 2, 0. Negative 5t plus 5 over 2 t, and then 0t we don't even need. So these are the parametric equations, and then this down here is the vector equation. So again, for part B, if you're given the equation of a plane, then what you want to do is you want to just sub in like random numbers for 2 of the variables, x and y, y and z, or x and z, and then find 3 points, and then find direction vectors. As long as the direction vectors are unique, then you can just use one of those points and any 2 direction vectors. So we're going to talk about determining whether or not planes are parallel or perpendicular, okay, and how we can tell. So perpendicular planes. What we know about perpendicular planes is that their normals will also be perpendicular. So if we have the equations or the, so like the A, B, and C, the coordinates, if we have 2 normal vectors, what we can do is we can dot them, and if that dot equals 0, then we know that they're perpendicular. Okay. Meanwhile, parallel planes, if two planes are parallel, what we know is that their normals are going to be some constant value k of like duplicates of one another. Okay. So what we can do is we can analyze them as normals or as kind of like a direction vector of the normal, and then we can see whether or not they're duplicates. So an example 4, I'm going to move this up right now. We're going to show that these two planes are perpendicular. So let's try that first. Okay, so we have plane 1 and plane 2. Okay, so these are both written in, should be Z there? These are both written in Cartesian, as a Cartesian equation. So plane 1 has normal. So let's call this normal 1. I'm going to write 2, -3, 1. 2, -3, 1. Okay, and then normal 2, let's call this 4, -3, -17. 4, -3, -17. Okay, what do we know about perpendicular normals? If we dot them, they will equal 0. So let's dot them. Let's go normal 1 dot normal 2. So 2 times 4, which is 8, plus, I'm not even going to bracket it, 8 plus -3 times -3 is 9. And then 1 plus 1 times -17 is -17. So our question is, does this side equal 0? Yes. 0 equals 0. Therefore, these, we can say pi 1, so plane 1 and plane 2 are perpendicular. Okay, let's move on to B. We have to show that plane 3 and plane 4 are parallel but not coincident. Okay, so normal 3 is going to be 2, -3, 2, 2, -3, 2, and normal 4 is going to be 2, -3, 2. Oh, well, that's really easy. Okay, 2, -3, 2. So therefore, plane 3 and plane 4 are parallel. Here's the thing, since they both have the same normals right there, we can just flat out compare that D value. So D of equation 3 is -1, and the D of equation 4 is -3. Okay, these are a multiple of 1. These are not a multiple of 1. So we can say but not coincident. And we can formally write these as N3 equals, actually we can just say N3 equals N4. Okay, D3 does not equal D4. And that's how we'd write it. If this was like 4 times, we would stick a 4 in there, but we don't have to because it's not a duplicate. It's not a multiple. Simply, the normals are exactly the same. Okay, so now let's talk about angles between intersecting planes. So if we have two planes and they intersect, if we want to find the angle between the two planes, so this right here, we'll call it theta. Let's consider their normals, so N1 and N2. We can calculate the angle between them using this equation right here. Cos theta equals, we're going to want to dot the normals, and then we're going to want to find the magnitude of the normals on the bottom. Okay, so let's determine the angle between plane 1 and plane 2. Okay, so first let's write the normals out. Normal 1 is 1, -1, -2, and then normal 2 is 2, 1, -1. Okay, so if we take a look at this equation, what we want to do first is we want to dot the normals. So I'm just going to dot the normals small down here, N1 times N dot N2. Okay, 1 times 2 is 2, plus -1 times 1 is -1. And then plus -2 times -1 is plus 2. Okay, we don't need the bracket. 2 minus 1 is 1 plus 2. I get 3. Okay, so in the equation, 3 goes on the top. Now let's find the magnitude of n1 and the magnitude of n2. Okay, I'm just going to do this down here as well. So magnitude of n1 is going to be 1 squared plus negative 1 squared plus negative 2 squared. So 1, 2, 3, 4, 5, 6, I get root 6. Okay, and n2, and I'm just doing this kind of like at the side of my paper, and then I'm going to actually sub it in and solve. Okay, 2, 1, and 1 again. So 2 squared plus 1 squared plus negative 1 squared. So it's 4, 5, 6, I get root 6. So I get root 6 times root 6, but we know that root 6 and root 6 is just 6. So I get cos theta equals 3 over 6. So I have cos theta equals 1/2. Okay, if I'm thinking about cos theta of 1/2, I'm thinking special triangles. Okay, so let's just go 30, 60, not drawn to scale. Okay, so cos of 1/2, I get 60. Theta equals 60. You can also just probably put that into your calculator and solve that. So the angle between these two planes is 60 degrees.